Alright, so this is lesson 5 for energy. We're going to be doing latent heat today. So what is latent heat? So I have a cooling curve down here. Let's just look at that first. Well, I should say it's a heating curve, because you don't really cool anything, you just lose heat. Okay, or you lose thermal energy. Right, so in here, what we have is, let's use water as an example. Water is easy to work with. So over here, we have ice. Okay, and so this, our x-axis is time, our y-axis is temperature. Now if we heat something up with a constant power, what happens is the ice, which is, I don't know, let's say minus 30 degrees, really cold ice, right? It's going to heat up. Now this has both kinetic energy and thermal energy as it's being heated, and then it reaches 0 degrees. Now we're continuing to transfer thermal energy. We're continuing to use a constant power source to heat up the ice, but its temperature isn't increasing anymore. So where's all that energy going? Where it's going is it's going into breaking the chemical bonds. So from being a solid, which would look something more like this over here, lots of bonds, to breaking a bunch of them to turn it into a liquid. So it actually takes quite a lot of energy to do that. So you can see as we are continuing to transfer energy at a constant rate, it's not increasing in temperature. So none of that energy is going into the kinetic energy of the particles. It's all going into the potential energy to break the bonds. Once those bonds are broken and we have a change of state, it's now liquid, so liquid water. Then you can see the temperature starts to increase. So that thermal energy transfer that we're doing with a constant power source is gone back to increasing the overall kinetic energy of the particles, and so its temperature goes up, up, up until it reaches 100 degrees. That's the boiling point of water. And then the temperature doesn't increase anymore. So once again, the energy that we're transferring, right, the heat, is not going into the kinetic energy of the particles. Now it's going to go into breaking more bonds. So it's going to break these bonds until it becomes water vapor. So until it becomes a gas. So it changes state once again. And then if we still end up heating it once it's fully changed state into a gas, then the energy that we're transferring goes back into the increasing the kinetic energy of the particles, and the temperature once again increases. So what we've learned before is the amount of energy required to increase the temperature. If you remember, Q equals mc delta T. That equation is good for here, here, and here. Doesn't work for here because we have no change in temperature. There is no delta T. So today we're going to learn the equations to actually calculate the amount of energy required to change state, either from a solid to a liquid, which we call melting or fusion, or from a liquid to a gas, which we call vaporization. Now to do that, let's start with fusion, right? Or melting. So the amount of heat required for fusion, so notice I have Q, right? And remember, heat is the energy transferred. So Q is a unit of energy. For fusion, so subscript F, is equal to the mass. Now that's important, right? Obviously, it makes sense that you would need more energy to melt more ice. And then we have this constant. Right? Now, similar to our previous lesson where we had mc delta T, we had that C, that specific heat capacity. This is something similar. This is called the latent heat of fusion. And it's the amount of thermal energy required to melt 1 kilogram of something. Now that something is important. So just like our specific heat capacity, it's different for each substance. So for aluminum, it's 6.6 times 10 to the 5 joules per kilogram. So that much energy for each kilogram. Now we have a very similar formula for vaporization, but you'll notice the only difference is the subscripts. Right, so the heat for vaporization, so we do subscript V, equals mass times the latent heat of vaporization. Now, very important, latent heat of vaporization, it seems similar to fusion, which it is. Right? It's the amount of thermal energy needed to vaporize 1 kilogram of a substance at its boiling point. But very important, it's not the same. LV is not the same as LF. So if you look at aluminum, its latent heat of fusion is 6.6 times 10 to the 5, and its latent heat of vaporization is 4.0. So you have to know whether or not you're turning something from solid to liquid or from liquid to gas. That's important. Right, so before we do some sample problems, a couple things I also wanted to mention was how we're going to heat it. Now, before, when I showed you the heating curve, it was linear. And that's because I was saying we were heating it with a constant power. So it's like putting something in your stove. Right? You turn the stove on high, it heats it with that constant power. However, if you pulled something out of your fridge and just set it on the table, it's going to heat it or cool it, depending on whether or not you have a hot cup of tea or a cool glass of milk, to a fixed temperature. In this case, if it's sitting on your table, it's going to heat or cool it to room temperature, for example. In that case, it's not a constant power that's heating it, and so our graph doesn't look as linear. It looks more curved. Okay, and now another thing I mentioned is entropy, or heat, always goes from hot to cold. If you wanted to go the other way, you have to do work on the system. Okay, remember, work is adding or removing energy from the system. In this case, we're going to have to add energy, right? Because if we want to go the opposite way nature intends to go, we need to force it to do that. So there are things called heat pumps, which add energy into the system to be able to remove heat from something cold and put it into something hot. Now, you know what heat pumps are. You have quite a few of them in your house. For example, a refrigerator, an air conditioner, and so on. Okay, so looking at some problems, our first problem says gold melts at 1064 degrees. It takes 5.5 times 10 to the 4, so 55,000 joules of energy to melt 50 grams of gold. Let's change that right away because we want that in SI units. So that's going to be 0.05 kilograms of gold at this temperature. Determine the specific latent heat of fusion. So basically what this is saying is we melted gold at its melting point using this much energy for that much gold. What's its latent heat of fusion? So the equation that I showed you was like this. F equals m times the latent heat of fusion. Now in this case, they're giving us Q. That's right here. That's the amount of energy. Q is energy. And they're asking for the latent heat of fusion. So we're just going to rearrange that equation and say LF equals QF over M. And then we can sub in what they tell us. So QF is 5.5 times 10 to the 4 joules over, and the mass is 0.05 kilograms. And you put that in your calculator, you'll get 1.1 times 10 to the 6 joules per kilogram. Now, something to be aware of is in certain textbooks or certain charts, when you look up latent heat of fusion, instead of giving you joules per kilogram, they actually give you kilojoules per kilogram. And in this case, that would be 1.1 times 10 to the 3 kilojoules per kilogram. So be careful with your units. Now, question 2 says the boiling point of ethanol is 78.4 degrees Celsius. Okay. calculate the quantity of energy. So it wants to know energy. That means we want to solve for Q. Needed to completely vaporize this much grams of ethanol. So let's change that into kilograms. So 0.075 kilograms. If its initial temperature is A, so let's do part A, 78.4 degrees. So if the ethanol is already at its boiling point, to figure out how much energy would be required to vaporize it, we're just going to use our latent heat of vaporization equation. QV equals mLV. And the mass is 0.075 kilograms. And the latent heat of vaporization, it tells us, notice, kilojoules per kilogram. Okay? We can leave it like that. But you just have to remember that if you leave it like that, your answer is going to be in kilojoules, not joules. So it helps to always make sure you put in your units so you know what you're getting out. Kilojoules per kilogram. Right, so you can see kilograms are going to cancel, and we're left with kilojoules. And this will give us 64.05 kilojoules. So part B is a little different. It says its initial temperature is 22.4 degrees. That's not at the boiling point. So you have to go back and remember your heating curve. So if you have ethanol here at 22.4 degrees, what we first need to do is bring it up to the boiling point of 78.4 degrees. So we need to heat it to that temperature. And that's a temperature change. So we're going to use the equation we learned yesterday, Q equals mc delta T. But the question isn't asking how much energy is required to bring it up to its boiling point. It's how much energy is required to completely vaporize it. So we need to boil it as well. So we need to add the energy required to actually vaporize it into a gas. And that's going to be what we just calculated in part A. The heat of vaporization. So we already know that. It's 64.05 kilojoules. So to figure out the total energy required to completely vaporize this ethanol, if its initial temperature is 22.4, we need to find the heat required, or the energy required to bring it up to its boiling point, and then we can add the energy required to actually vaporize it. So let's solve for this. We know the mass is 0.075 kilograms. Its specific heat capacity tells us, and again, be careful, it's telling us kilojoules, not joules. So make sure you keep your units so you know what you're getting out of it. I wrote kilograms. Let me fix that. And kilojoules per kilogram. Now it says Kelvin, but again, it doesn't matter. It's the same thing because it's always a change in temperature that we're looking at here. So I can just write degrees Celsius. It would be the same value. And our change in temperature, we're going from 22.4 to 78.4. So always do final minus initial. So 78.4 degrees Celsius minus 22.4 degrees Celsius, and you put that in your calculator, you'll get 11.42 kilojoules. Right, so now you just need to find the total. So the total heat required to completely vaporize the ethanol from an initial temperature of 22.4 equals the amount of energy required to bring it up to its boiling point plus the amount of energy required to actually boil it. And look at the difference. Right? The amount of energy to actually vaporize it is way more than the amount of energy it took to bring it up to that boiling point. So that tells you there's a lot of stored energy inside those chemical bonds. And so when we find the total, we get 75.47 kilojoules. There you go.